This lab experiment examined the effects of moving air on a cylinder in the wind tunnel to observe flow separation and the highly unsteady flow field being generated in the cylinder's wake. We performed the experiment at multiple flow conditions: wind tunnel velocity at 15 and 30 meters per second, and with trip strips on and off the cylinder. A scanning valve device was used to measure pressure data and drag at 2 different Reynolds numbers on the cylinder. We also utilized smoke from a smoke machine at the inlet of the wind tunnel and a green line laser from above to help create flow visualization of the airstreams around the cylinder and the vortices being generated behind the cylinder due to boundary layer shedding. The results showed that when the speed of air flowing around the cylinder and the Reynolds number was low enough, the boundary layer stayed intact and attached to the cylinder. As the airspeed and Reynolds number increased, the boundary layer started shedding and a pattern of vortices started appearing in the wake of the cylinder. These are the variables we are going to be using in our lab report.
In this experiment, the Cal Poly low-speed wind tunnel was used to evaluate the boundary layer as it formed along the surface of a cylinder that was placed in the flow. The wind tunnel was run at 4 different RPMs. Each speed was tested twice for accuracy. After the data was taken for the standalone cylinder, 2 trip strips were added to the surface equidistant from the stagnation point. These disturbed the flow and created a vortex shedding that disturbed the boundary layer. With the trip strips attached, the same values of RPM were tested to ensure accuracy when comparing the boundary layer before and after the strips were added. In order to properly analyze the boundary layer and its detachment from the surface of the cylinder, pressure ports are located around the circumference to measure the localized pressure at each point, giving an insight into when the flow detaches. For the same purpose, a smoke machine and laser combination was used to visualize the shedding as the smoke flowed past the cylinder and was illuminated by the laser.
As mentioned before, the Cal Poly low-speed wind tunnel is the main apparatus used to move large quantities of air through a 1.19 by 0.87 square meter test section. A circular cylinder with length equal to that of the test section width is suspended in the middle of the test section height. The surface of this cylinder is smooth, with 24 pressure ports spanning across the cross-sectional area, each 15 degrees apart. The first port is 15 degrees above the horizontal axis on the section behind the cylinder, such that port 12 is directly in front of the flow. The scanning valve device is used to record the pressure readings, which sends this data to a LabVIEW program. A smoke machine is placed at the inlet of the wind tunnel so as to create a stream of visible particles moving through the wind tunnel and around the cylinder. To visualize this further, a green laser is used to shine a sheet of light, illuminating a portion parallel to the fluid flow. After conducting the experiment with this test setup, the 2 thin sandpaper strips are attached to the cylinder in 2 locations, one between ports 8 and 9 and the other between ports 15 and 16. The results from these 2 experiments are then analyzed to understand the nature of this airflow.
These are the equations that we are going to be using in the analysis section. The Strohal number is a dimensionless value that describes oscillatory patterns. The second and fifth equations relate to drag coefficient. Drag coefficient is used to quantify the drag or resistance of an object in a fluid environment. The Reynolds number is a dimensionless quantity used to help predict flow patterns in the different fluid flow situations. Specific heat capacity at constant pressure characterizes the amount of heat required to change a substance's temperature at a constant pressure.
In the plots of coefficient of pressure versus drag, we see that with the trip strip, the minimum coefficient of pressure moves 1 pressure station, or 7.5 degrees, away from the stagnation point. This is evidence that the flow is staying attached to the cylinder for a longer distance. The coefficient of pressure decreases because the dynamic pressure increases as the flow accelerates. The trip strip successfully increased the amount of attached flow, but at the same time increased drag. Since the flow is attached for longer, it creates a larger low-pressure zone than the cylinder without the trip strip and thus increases drag. We calculated drag using midpoint Riemann sum summation of the integral that calculates drag. We used the midpoint as opposed to the left or right because this gives us the best estimation of drag at each point. Using the left or right angle would result in asymmetrical drag along the top and bottom. At 15 meters per second, the drag increased by 24.1%. At 30 meters per second, the drag increased by 31.1%. The drag increases more at 30 meters per second because the ratio of static pressure over dynamic pressure is higher. We expect this trend to follow for increasing velocities, but more testing focused on velocity change would be necessary to confirm. The coefficient of drag increases once we add the strip. This is expected because our drag increased with the same velocity and Reynolds number. We see that the coefficient of drag versus Reynolds number follows the expected trend. However, we would need to test at a wider range of Reynolds numbers to confirm.
This video describes the airflow that is seen in front of the cylinder at a wind tunnel speed of 2.7 meters per second. It is possible to see the stagnation point at the front of the cylinder. Additionally, the separation point at the top of the cylinder can also somewhat be seen. In this video, it is easier to notice the bounding layer that forms around the cylinder. The air that is closer to the surface of the cylinder can be seen traveling slower when compared to the air higher up. This video describes the airflow that is seen behind the cylinder at a wind tunnel speed of 2.7 meters per second. In this video, you can see the wake and recirculation zone that occurs behind the cylinder. Additionally, it can be seen that vortices form behind the cylinder and are oscillating. This is also called vortex shedding. This occurs because the separation point causes the boundary layer to separate from the cylinder, which then causes the airflow to become turbulent and recirculate. This is the cause of the vortices behind the cylinder. Additionally, we calculated the Strouhal number for this speed as 0.41. This low Strouhal number correlates to the instability of the wake that we see at this velocity. This video describes the airflow that is seen in front of the cylinder without the trip strips in place at a wind tunnel speed of 6 meters per second. This video also serves to show how a wake forms behind the cylinder in which the air can be seen recirculating. The airflow behind the cylinder is unsteady, and again you can see vortex shedding behind the cylinder. This video describes the airflow that is seen in front of the cylinder with the trip strips in place at a wind tunnel speed of 6 meters per second. The flow in the front of the cylinder is mostly steady. Additionally, it can be seen that the flow is attached to the cylinder longer. The flow can be seen going around along the cylinder. However, it is harder to see the separation point since it has been moved. This video describes the airflow that is seen behind the cylinder with the trip strips in place at a wind tunnel speed of 6 meters per second. In our MATLAB code, we talk about the separation zone being moved by 7.5 degrees at 15 meters per second. In this video, it can also be seen that the separation zone has been moved because of the trip strip. However, it is not exactly the amount in the MATLAB code because the code is based on a different wind tunnel speed. The trip strips act similarly to vortex generators, which are seen on cars and planes. These trip strips cause the air to become turbulent inside the boundary layer. However, this then causes the airflow to stay attached longer because the turbulent air mixes with the high-energy free stream air, which then causes the air inside the boundary layer to become energized. This energized air then stays attached to the cylinder longer as it can withstand the pressure gradient, which would normally cause it to separate. However, the trip strip is not exactly like a vortex generator because the trip strip increases drag around the cylinder. On the other hand, usually vortex generators reduce drag. However, since the flow is attached for longer, it creates a larger low pressure zone than the cylinder without the trip strip and thus increases drag.
We wanted to observe how flow would look like at a higher speed, so we decided to test at a wind tunnel speed of 16.7 meters per second. Here, we can clearly see the separation point from the cylinder. When the airflow separates, it becomes highly turbulent, which then creates a larger recirculation zone.
This video demonstrates an issue that we had with our trip strips. Multiple times the trip strips would come off during testing.
The purpose of this lab was to visualize the separation of the boundary layer off of the cylinder at multiple wind speeds produced by the low-speed wind tunnel. Both with and without trip strips, which act similar to a vortex generator, the separation point of the boundary layer was moved, allowing the flow to stay attached longer when compared with before the strips were added. This increased the drag experienced by the cylinder. The drag was a resultant of the increasing air speeds the cylinder was subjected to, which also had the same effect on the Reynolds number of the test piece. Visually obvious when analyzing the videos of the test is the presence of vortex shedding and flow interactions as the boundary layer detaches at different points depending on the inclusion or lack thereof of test strips.